I try to just give you all the information. So, do you remember where we were last time? Proof. We're about to start the proof. We're talking about activity selection. Do you guys remember? So the general idea was that if you have some sort of space, what was the variable? Some set, it's A. And A is a bunch of activities with different start and finish times. And I think each activity, so you had, this is kind of the problem definition, where this is better, right? It's a little bit bigger this time. You don't have to rewrite this via from last week. I'm just going to recap. Each activity has a start time and end time, so SI and FI. SI and FI are both positive integer values. I don't know if zero's in there or not, I can't remember, but maybe it should just be the numbers, the set of numbers. Whatever. And what else was there? Oh yeah, SI is always less than FI. So that was the basic problem definition, and given that you want to populate a set, and we changed the name, it was started as S, but then I realized S was used twice. So we want to populate a schedule set, which starts out as empty, with the largest possible set of mutually exclusive activities, like the largest set of non-conflicting activities. And the question was, how can we do that? We figured out that it turns out that if we have an overlap function, so AIAJ, that indicates whether or not things are overlapping, that we can just greedily loop through and look for the finish time of activities and just grab those finish times. If they don't overlap, then they can make it into the set of L. And our belief is that that is actually optimal, and the question today is whether or not we can show that it's optimal. And it turns out it's going to tell you yes, and we're going to do it right now. And I think it's really cool. Are you guys pumped? Yep. Was that okay, cool. Yeah, so the question is, well, I guess I could pose it to you. Is there more than one optimal solution to this problem, do you think? Given a set of an arbitrary set of activities, is there more than one optimal?
Yeah. Yes.
Okay, so we might want to somehow denote the family of optimal. I like using set notation. I don't like writing a lot of text, so I'm not going to write there are multiple optimal things. I'm just going to write a set definition. So I'm going to consider all optimal sets or schedules. So that might look something like, So we're going to call it capital OPT. I kind of hate that, but that's just the way people do it, so we're going to go with that. So there's probably an optimal set, or there are a family of optimal sets that may or may not be, or that are a subset of A. And they all have one characteristic. Make this big. With the terrible sigma. J. Yeah. Or you just have this property. Last week someone pointed out that I was missing a property here. Does anybody remember what it was? I forget. This is a pretty good starter. Oh, the empty one, n is not empty. Non-empty. So basically, all I'm saying here is that there's a family of optimal sets that are a subset of A, right? So whatever we're going to talk about as optimal in a second is going to be something that's a subset of A, such that it has no overlapping items. If you sum, so overlap is an indicator function that's in 0 or 1. So, and all we're going to say is that as we look at all the different combinations of sets, that there are a family of sets that are optimal, and we're going to denote each instance of it as optimal. So if I say OPT, it's just something that fulfills this property. Does that make sense? But when I write it, I don't mean every one of them. If I meant every one of them, I would say something like the family of all optimal sets or something. But we're not even going to talk about that. So if we're cool with that, is that weird? Is that terrifying? Does it make sense?
Sorry, can you just repeat what you mean by OPT?
Yeah, it's just a variable, so it's like x. So all I'm saying is that when I write down x, then I'm talking about the schedule. So I'm talking about a specific arrangement of items. So it might be, so an example of OPT. An example of OPT in this set here. Actually, I think it's exciting. Let's give 2 examples that we can just do by inspections. This is A, B, C, and D. So OPT, there's going to be 2 of them. Actually, can someone tell me one of the optimal sets? ABD. Yeah, ABD. So OPT, one of the OPTs might, so let's say OPT A might be A, B, D. Does anyone see another one? I'm not thinking. You already got one.
ACD.
Yeah, ACD. So it's the ones that work it's the ones that don't overlap. So it's all the combinations in the set A that don't overlap. That's all. But it's nice to be able to say it in a specific way so that later on we can draw on that if we want. And it's always nice to set up notation that's advantageous if you can think ahead. And sometimes think backwards. You're working through a problem and you realize like, oh, this weird concept is like two sentences long to explain. I wish I could say it in one word. And that's when you can go into the past, well, up a few lines, and instance a function that describes what you're talking about. And you're always allowed to do that, and it can help you reason through proofs, it can help you reason through problems, so that you can kind of clear your head. Same thing with the overlap function. It's just a function we make up so we can talk about overlap in a really clear way so we don't get lost. Otherwise, just say such that the start time and end time don't cross in this way, and then you have this giant sentence and talk about a simple concept. Yeah. Is that cool? I'm going to take it. Silence as yes. Perfect. Okay, so anyway, so given that family, so imagine we have something like opt A. So we have this, and the idea is, well, what makes it optimal? Is there something we can say about it that we can use later? So when we ended off lecture last time, we were talking about the fact that as our recursive algorithm, or as our iterative algorithm's running, that we're slowly building L sets. We have these L sets. Then L0 is of course empty. And then L1 is going to have some sort of A1 in it, right? Or A1, so A for iteration 1, where I equals 1. L2 will have A1 and A2, and so on, right? And the idea is that what we believe our algorithm does is that given L0, L1, L2, all the way to Ln, we believe that at Ln, that Ln equals optimal. So does anybody kind of like start to see an interesting thing here when you have Ln equals optimal? What do you think about the set L2, for example? Does it relate to the optimal set?
It's optimal up to that point.
Yeah, like, I mean, any set that, as you're growing your set, as you're iterating through your algorithm, you would believe that you're building towards the optimal set. And that's essentially the argument we're gonna think about. So that's one way we could do it. The other way we talked about was that given the optimal set, we might be able to break it into sub-problems, and that we might be able to somehow have some sort of recursive definition or something there. But the other way to think about it is like, okay, well, we have an optimal set, and we know that everything up to that point has to be a piece of the optimal set. So then one way to think about it is like, well, let's talk about breaking our optimal set up and see what it looks like. So we know that at some point, let's see here. So we'd almost like to be able to define a set as promising, or as like a set that's going to turn into something, like it's got potential. And so we already know that that is probably a set that's building towards something. And it turns out that if we're careful with our like, for example, if we take the set L0, it's empty, right? Forget about the empty for a second. And if we take the union of that set with the optimal set, with an optimal set, I should say, what does that equal? It's kind of a weird, silly question. Yeah, so it's empty. So it turns out that when we have nothing going on at all, that we can just take the union and we can have the optimal set. It also turns out if we take L1, and we know that the optimal set is a sequence, right? So if we have this special L1, and we have this property that if we, how do I say this? If we have L1 plus the optimal set from, so this is I equals 1, right, here? So if we take the second element in the set all the way to n, so if we use this, what I'm doing here is I'm setting up the notation to say that this is the optimal set from index I plus 1 to n. So if we treat the set as a sequence, like, you know, A1, A2, A3 to AN, where there's an AI here. Does it make sense so far? Stop me if it's like super confusing. I would love if somebody was like, I am totally confused.
Sorry, come again, what's the subindex notation there? What is it?
Yeah, so it's just like I
comma.
plus 1 to n, where n is the end of the set.
Okay.
So the full set, the full optimal set would be denoted. So the full set, we can call, let's call the full set, I don't know what it is. One to n. So this is equivalent to OPT. You can also say with this notation that OPT 1 to j, or 1 to, like, let's just make a new index k, union OPT k to n equals. Sorry, does that make sense? No? We're just kind of like cleaving the set at a certain point in the index. And we're assuming that the optimal set could have been built from beginning to end, and we're assuming that our L set might build that set.
What's I?
I is an index, so an index.
So in that case.
So in this case, it's sorry, yeah, I guess it'll be. This is 1,
Yeah.
so this would be 2. Sorry. And in the general, and so we're saying that if we do this, that this might equal the OPT set, right? And this is kind of this is like a situation we might call, this is like for L1, it's got one activity in it, it's the first iteration into the algorithm. So we've made one iteration, and L1, if we union it with an optimal set, and it turns out that if we take the rest of if we had a hypothetical rest of an optimal set, if it turns out that's the same as the optimal set, this is pretty good, this is promising. Right? Is that sort of clear so far? I know I'm being a bit clunky. I'm not putting as many words on the board. I might revert to more words. If it's too confusing.
In that case, you will be
Sorry?
will need L0.
Yeah, it's true. It's true. So fair enough. But L0 is empty, so it's kind of being a bit cheeky. Yeah. And also, actually, L2 will be the set from 0 to 1. So L3, the L set at L3 will include the elements all the way from 0 to 1. So it's not just a snapshot at that time. That would be the element at L at iteration 3 is like A3 versus the set that's built by the algorithm is L. It's the schedule up to that point. Cool. Okay. So we have this idea, like this is a weird idea to use. Like it's already pretty confusing. When you first start looking at it, like, okay, well, obviously the optimal thing is going to be built on a previous optimal thing, but I don't know what the optimal set is. So it can seem difficult at first how we can use that. But I'm going to put the more formal stuff here now, based on this idea that we have an idea of what promising is. Yeah. More formally, we can say that a set, Li, is promising. So you can say something is promising for some set Li if, and then what we can say is Li is a subset of Li union the optimal set from iteration I plus 1 to n. So I've kind of built up this weird language over here with you guys, just so I can say this. So I want to say that something's promising when the current set that we have at Li turns out to be, if we take its union plus the optimal set, for an optimal set from I plus 1 to n, that this, equals OPT, sorry, this equals, oh no, that's right. This is correct, yeah. So this set turns out to be a subset of this set union the optimal set. And that this equals OPT. We kind of know that though, but I'm gonna say it anyway. Does that sort of make sense? Because we're gonna use this function. Just means that this bit here, Li, is optimal. So what does this mean? Specifically, this means that it's optimal. Is good, is promising. A specific example might be if we have A1, A2, A3, right? And then at this point, so this can be our L3, right? And then at this point, we have kind of a fuzzy future. So we might have a lot of blocks, right, which we might consider in our A set, but we know A set has a lot of optimals, right? And we might have a certain optimal here where all of these guys are in the optimal set. So as we march forward and we pick specific ones, we're in a good situation if going forward, what we've done turns out to be part of the optimal set. Is that a little bit easier? A little picture? A little picture helps out? No? The fun part's about to begin. Yep.
Isn't your promising Li, isn't that just the same as Li is a subset of optimal? Why do you need to union it with Li?
You'll see in a second, because we're going to use that idea that we can take where we've been plus where we're going we're going to use it in induction, basically. So we're going to want this idea that we can identify the promising set as a subset of the future optimal to get somewhere. So it seems like, why would you say that now? But it's because we have an idea. And what actually usually happens in practice is you have the idea and it's complicated, and you simplify it to that form afterward. Do you know what I mean? Like you have an idea, you work it out, and then you're like, well, how can I write this in natural language? And you have to work backwards to find out the most precise way to say it. If that makes sense. It's kind of like if you take a lot of notes for an essay and then you boil it down, into like a good introduction.
It's an if and only if relationship,
I think, do you mean for, yes, it's if and only if. Yeah, but I'm not being too precise about it, but yeah. But we have to be careful because this is one particular optimal, right? So this whole time, be really careful because we've been talking about the idea there's a family of optimal sets, and in the notation over here, I'm just using one of them. So there could be like 100 of them. So we could put that down, and then someone could say, oh, hold on, there's OPT prime, and it's not a number of OPT prime, it's still optimal, it is. So I guess it's not if and only if. Everyone has this, right? Yeah.
All right.
This is the cool part, guys. All that setup, and you're like, what's going on is for this. So now let's sit back and let's think about the set L0 as our sort of base case. So for the proof, we're going to use induction. Our base case will of course be L0. Is L0 promising? Yeah. So it turns out this is promising. I would say 1. So that's good. Good start, right? We're not done yet. So for our sort of inductive hypothesis, will be that for the time indexes greater than or equal to 0, we're just saying that it's always promising. Saying that as our algorithm runs, it's always promising. And that's our big sort of, our way to concretely state in formal terms what we mean by the algorithm that will build the optimal solution, that will come up with the optimal schedule. So I think if we say we have that set, and that it's promising if our current set is a subset of one of those, then it's promising, right? Like it's clear. So far so good, I think. Yeah. So what happens at iteration I? What does our algorithm do? From iteration I to I plus 1, what's our algorithm do? It's going to make some choices. Does anybody have an idea? Like, what's it going to do? Someone's got to tell me. So we have a candidate set of activities, A1 and A2 and A3, and we're moving to A4. Or perhaps. So at iteration 3, what's our algorithm going to choose to do? Does anybody have an idea of what some of those options are?
We're doing greedy by finish, right? We're doing greedy by finish time, right?
Yeah.
So it's gonna take the
Oh no, we're reading by finish time, yeah.
Yeah, so it's gonna, we already sorted by
we're sorted.
by finish, so we're just gonna grab the next activity that will finish the soonest.
Exactly. So so our algorithm, pretend we're given a candidate activity. Let's call it just A. So we're given an activity A. What will the algorithm do with activity A at iteration I? So you've got this set that you've built, and you get a new activity. What are some of the things that the algorithm might do with it?
Oh, it's gonna check that it's not gonna have an overlap with the.
It's gonna check whether or not it has an overlap. Anything else?
Check if it has the earliest finish time.
It's gonna check if it has the earliest, yeah, and that's by virtue of the fact that it's sorted, right? But technically, the algorithm will, in its processing, it checks whether or not the finish time is earliest or not. But that's, yeah, by virtue of the sorting. There's really two sort of choices going on. And I don't know if you guys remember from last time, but we sneakily defined a function called choice. So we're gonna use that function now. So at iteration I, the alg will make a choice. And we're just going to call this choice of action, AC equals choice L, or of, Li. So given the previous set and at iteration I. So this is actually from Li moving to Li plus 1. So given a previous set, and I'm also assuming that there's a new activity in the A queue, but I'm not putting A in there. It's just too much writing. We're saying at iteration L or at iteration I, given the previous history and this set A. So we're assuming a set A is in there. There's like some context. We're going to come up with a choice of a new action, and that's the choice our algorithm is going to make. Do you guys remember the algorithm? Is it helpful to write it up? Like, is it totally confusing if I'm talking about an algorithm that's not on the board? Or is it okay? Like, you understand that we're doing a loop and we're looking for... It's okay? Okay. I saw one nod and I was satisfied with that. So, given our hypothesis and the activity that our function can take, we're going to do an inductive step now. We're going to consider our inductive step. Right? We're going to attempt to show that Li plus 1, when we're basically going to show that, and I'm going to put this in the line. That Li plus 1, which is equal to Li unioned with the AC, with our chosen action, right? We're going to show that we have this property and that we still have the promising for Li plus 1. Sorry, I got a little crunch there. Does that make sense? So now we have something that we can kind of work with. We have this idea that we're going to step into a set, right? Where if we take the union of that set plus our current choice at iteration I, so we look forward to I plus 1. If we take the union there, then we're going to end up with a set that is still promising, that is still a subset of an optimal, of that optimal we're considering. How do you guys feel? Great. Okay, good. Just gotta placate me with every once in a while with some nice words. All right, so let's consider some. I'm gonna put it on this board just because I want to put it up after. You guys don't need this anymore, right? This is a little old. Okay, so, yeah, at this point we have some choices. So, at iteration work up here. What are some of the cases? Does anybody want to enumerate some for me? So we kind of mentioned them already. What's the first most simple thing that can happen? So we'll call it case A. Is that AC, that the algorithm chooses that AC is empty. Meaning, so if the algorithm chooses an empty action, if it chooses an action that doesn't exist, this is kind of not popular, I guess, the front row. We're saying that Li is equal to Li plus 1. So the question is the Li plus 1 still optimal? If we believe our hypothesis up to this point, is Li plus 1 still optimal? It's trivial, right? Like, because we already know we have the optimal property, so the step before at Li we were already promising. We've assumed that. If we add nothing to the set, it's still promising. Right? There's a little more we can say about this. What's the condition that is satisfied when we don't include an item? There's only one condition that can cause a loop to go on, to execute, and for the choice to be empty. What is that condition?
It overlaps.
No, not yet. We got a few more iterations to go. Overlap, yeah. So the condition, so we're not quite done here, because what if the algorithm just runs and never adds anything? Or we're not really building a set. So we have to analyze, well, what's happening here? Like, why isn't it adding anything? It turns out it only doesn't add something, only happens when overlap, right? I'm going to use some jerky notation here, which isn't quite right, but I'm going to say the overlap of the action or of the item considered at iteration I by the algorithm, and the set Li equals 1. So what does this look like to you if this condition arose? It contradicts the thing I erased. Contradicts promising.
I think that should be I plus 1.
Sure, yeah, it should be I plus 1, actually, you're right. So it would have been this. If we added an item, if the algorithm falls into this step, it's avoiding a situation where the overlap would have been 1, right? And that's the only if statement that falls in there. So right now we're considering the first if statement in that loop, is that it skips over. Right? So we know that's good. So let's consider the other result of the if statement. The other result of that if statement, so maybe I'll even do this. We'll call it the if overlap. So at least the case 1, then we're going to consider case 2, where if overlap equals no. Okay? So in case B, what are we going to do? What happens in case B? So we have an AC. We have AC equals some item. I don't really have a good notation to it. So I'll just write what I wrote in my notes. What I wrote was we have Li is extended to equal such that Li is the Li plus 1 equals Li union with our choice. Does that make sense? So that's the other side of the if statement. The first side of the if statement is that if there's an overlap, we don't add it, and that's good. It's good that we don't add it because it's going to lead to a contradiction. So that functions well. We're not going to add things that are overlap. Perfect. Because that's we're guarding the first property of our set. Fine. And it turns out that all the algorithms did that. If we think back, none of the algorithms, even though they were suboptimal, none of them ever added overlapping elements. So that's pretty good. Like, we're not double booking the rooms, right? But then we have this next condition here. So is this sufficient just to say that this is optimal at this point? Like it's adding items, so it's perfect. Is there anything we have to think about with AC? This is kind of the crux of the proof right here. It's like when we've selected an AC, our algorithm has selected the AC, what do we want to know that the new AC is? What's, We want to know if the AC is going to be part of the promising set. We want to know if it's on the way to the optimal set. That's what we want to know. This is the core question. Okay, our algorithm's made a choice. It's made a selection for we're at Ally. We're considering the next room booking. We want to know if Ally is in promising. Right? And we know there's multiple optimums. So this is where things can be a little bit confusing. But it turns out that if you think about it properly, and since we've set up our notation in an advantageous way, we can think about it. So there's two subcases here. We'll say BA. BA is that, and this is a simple one, yeah, that the new action is equal to our previous AA plus 1, which is in the optimal set, right, from I plus 1 to n. So this is good, like this is fine. So that's one option. One option is that at this point, we're going to automatically choose an AC that's optimal. So that probably will happen. So that's good. Does that always happen? Does it always happen that we're going to choose the schedule that we're going to choose them from the optimal set? Is that a thing that we can expect? Let's think about it. This is the part that requires some thought. So we have some schedules here. Write them out. Did I draw them? Let's make this nice, actually. Let's just make this really simple. Okay. So, I know that's kind of weird. Is that bottom, is this subset of all the activities A, is this optimal? Yeah. Is the other one optimal?
Yeah.
Okay, so if we name this one OPT, right, and then we name the other one OPT prime, they're both promising, right? So that's essentially where we're going. We're thinking, okay, well, even if I choose something that finishes earlier, it still starts after this one. It still starts after because we're not adding things that overlap. So even if we choose something that starts earlier, we're just going to sub it out, and we're still going to be building an optimal set, and that's essentially going to be our argument in a second. Does that make sense? Mm-hmm. So it turns out that if you think about it carefully enough, you can realize that no matter what, as you're adding items greedily by the finish time, as long as you're not overlapping, which we're not, you will build the minimum set. Does that make sense? It's kind of cool. I think it's cool. Anyway. Yeah, so let's just write that out. I'll write it out up here so that you guys can see what we do.
So is case BA the case where the activity we chose is still actually building the optimal set?
Yeah.
Would you be writing later like case BB where the activity we choose is not building the optimal set?
That's going to go right here. Yeah. I just wanted to pause to like reason about it before we did it, so that it wasn't just like gobbledygook. Yeah, so case B is, broadly speaking, if AC is not equal to AI plus 1, which is in OPT, I plus 1 to n. So now we're considering the case that the chosen action is not equal to the next item in the optional set, right? And so what does this imply? This implies directly two things. Can I use 1 and 2 again? We haven't used any numbers yet. This implies that 1, so we're going to use the subscripts here for continuity. It implies that FC is less than or equal to Fi plus 1. And this is where we start to get a benefit from our notation, because we can say stuff like choice and all that, all these promising, these great words in a precise manner. It's also a mark of good programming to use functions that make sense when you read them. It turns out that in both cases, so the AC, we already know from previously that there's no overlap. So, right? And essentially what we're doing, what we're considering is, just going to rewrite this. Actually, I'll leave it, I'll write it a little bit. Actually, you know what? I'll finish this first. So this is, okay, so what we're doing is we're forming a new set. We're forming a new set. Right? And our new set looks like Li, right? Union AC, right? Union our new OPT I plus 2 to n. So this is kind of the new set we're forming. We're forming a new set, and it could look like this. It could be promising. Would you say that this new set, given everything we know, is still promising? What makes a set promising? It's a simple property, and it involves two double summations that we talked about earlier. It's involves summing over all the items and making sure there's no what. That's the only property. There's no overlap. Does this new set we're forming have an overlap? If the new item we're adding instead has the exact same finish time or earlier, is there overlap when we compare it with the new optimal set that we're building, or the previous optimal set? No, it's still optimal. It's still an optimal. It's still in the family of all the optimal sets that we talked about earlier. So we can say that we have some new optimal value prime, and this is the crazy mind-bending part. Is that we can now consider this new OPT prime that we might be forming as a new candidate for our optimal that we're building towards. Because it's exchangeable, it's in the family of the optimal sets. We just want an optimal set that's in the family of all the optimal sets we talked about earlier. We don't want this specific optimal, we just want to know that we're building towards an optimal, and all an optimal is a set that does not overlap at any point. Does that make sense? Am I confusing you? Feel free to tell me you're confused and I'll try to help you out. So yeah, so for iteration I plus 1, we just set OPT to be equal to OPT prime, and that's it. We did it. So, basically what we've done is we've analyzed the cases in detail, all the cases that the algorithm can fall through. So when we arrive at an iteration, we ask ourselves, do we have a new choice or not? We verified that if we don't have a choice, it's only because of overlap, and so we're still good, because that's exactly what the algorithm should do. Then we looked at the fact that Li is extended by one choice. We've chosen a new action for Li plus 1, and we looked at whether or not that new action was building towards our previously imagined optimal. And we verified that in the case that we're building a different optimal, it's still in the family of the optimal set, which is perfect. So it turns out that the algorithm's fine, and if we slowly work through it, it's perfect. Does that make sense? You probably have to sit down and work through it yourself, because it's a little bit confusing, but if you reason through it, it makes a lot of sense. And if we really want to hammer it, well, it's okay, I was going to rewrite that set.
Is Fi plus 1, like we have the FC, and so FC is the finishing time of the event that we chose.
No, FC is the choice. It's the same, FC is in the AC.
Yeah, so it's the AC's F.
Yeah.
Right. And so Fi plus 1, is that the finishing time of what would be the next one in our first optimal set?
Yeah, it's Fi plus 1 is the first optimal set here. It's in its AI.
Okay, so if this one's ending earlier, then that just means we're building another optimal set, we can still get just as many.
Exactly, because the core idea is that we're trying to maximize the amount of activity scheduled. So if we pick an earlier time for one of them, and it still starts at the same, it could still start around the same time. It doesn't overlap. It's fine. We still get the same amount of items scheduled. It's kind of weird. Makes sense? I would recommend, like, when I post the notes, I'd recommend sitting down and having it work through it slowly. And it's the kind of reasoning you'll have to practice, and it kind of hurts, but it's also fun. It's very gratifying. If you find it confusing. If you're like godlike and you don't find things like that confusing at all, then that's good. Do you guys have questions? Because next up is like a different subject. So if you guys want to talk in general about activity scheduling. Oh no! Went too slow. I was so excited for this next bit too. It's really cool. Oh man. Yeah, whatever. I'll do it faster next time. Well, guys, I timed it perfectly, so it's time to go.